And we'll go through a lot more examples. And I want to kind of skip between annealing and gate computing. So the way that I kind of look at it is quantum gate computing is really, if done properly and scales properly, is really what's really exciting, that it can mimic some of the behaviors of traditional semiconductors, your regular CPU chip or your GPU chip, but able to do a lot more calculations in a lot faster time. And there's this concept of reversibility, and we'll go through that a little bit. But the biggest thing is that from a speed standpoint, if you set the problem up correctly, it feels basically instantaneous as far as the solution is concerned, because you're being able to run all the possibilities as opposed to probabilities instantly. And so there's a whole bunch of different gates. Now, this is where I'm going to violate the rules and see if I can share a screen here. All right, let's see. Okay, so you should be able to see my screen, and this is the quantum experience at IBM on their architecture that you guys actually have the ability to look at. And we're going to look at the support. Let's see if I can click support here. Okay, so here's the thing. This is not a simple process to do. And the last thing you want to be doing is trying to do all these linear algorithms and transformations in your head. What you really want is an environment that's simple and easy to use so that you don't have to try to figure out everything from scratch. Now, although I wouldn't say from a personal utilization on a practical basis as of right now, I wouldn't be using IBM. But from a learning standpoint, IBM's done a pretty good job of creating an environment that allows you to teach yourself, different types of simulations of how to use a quantum computer. So let me see if I can open up. Okay, so the reason why I wanted to show you this, I don't know, can everybody see my screen here?
Yeah.
Yeah, we can see.
So this is a simple set of different types of quantum instructions. And we're going to go through kind of how an example would be. Linear algebra is a pain in the butt. But the reality is it's actually a visual like this gives you kind of an understanding of really what a different gate, a quantum gate instruction can actually do. So really it's taking data and transforming it within this concept called the block sphere. So there's all these different types of gates, and really what they are is different ways to transform that linear algebra or transform the data from point to point. Now, why does this actually matter? Think about the example of, traversing to Everest. You want to understand how you can traverse terrain through different dimensions. And these different gates allow you to actually take all that data and transpose it within a quantum environment to efficiently get there. So think about if you've got hands and legs and you can move up and down to a certain degree as a human. If you're going to go up and down a mountain. Well, it's kind of the same thing here. This quantum gate computing allows you to, within certain limits, use the concepts of quantum superposition to be able to just transform information from one point to one point. So it could be cross different axes, you can go vertical, you can go all the different directions. So that's my kind of way of explaining a bunch of these more esoteric concepts called gate instructions. So let me go back. All these different gates have fancy names like the Pauli gate, the Hadamard gate, Clifford gate. Really all you have to do is think about, like in linear algebra, like I said, if you try to keep everything in your head, it gets really complex. But I think IBM's done a great job of getting you to understand that really it's the manipulation of a particle within space, and how these gates and these manipulations allow you to transpose and transform where the position is. And that's that whole concept of superposition. So that's like the first step that you've got to understand.